In this video, we're going to go over neutral functional groups. If you haven't already, make sure you watch the first video on acidic functional groups, the second video on basic functional groups, before you watch this video on neutral functional groups. So our neutral functional groups are going to include alcohols, ethers, esters, amides and ester amides, ketones and aldehydes, and pyrrole. And with pyrrole, we're going to really dive into the difference between pyrrole and pyridine. And because if you remember from the last video, we had pyridines, and pyridines are basic. Pyrroles are neutral. They look very similar and they're often confused. So make sure that you really pay attention to that last one when we get there. So our first functional group is an alcohol. So for example, I could have an alkyl chain attached to an OH group. And then you might be wondering, well, why is this neutral? Whereas something that looks really similar to it, a carboxylic acid, why is that acidic? So why is this carboxylic acid acidic, but the alcohol is neutral? And the reason for that is that if you remove this proton versus removing this proton, you'll end up with a completely different conjugate base or IB form. Okay, and so if I remove a proton from that first structure, I end up with an oxygen with a negative charge on it. Now, if I remove an oxygen from that second structure, if I remove a hydrogen, a proton, from that second structure, the carboxylic acid, I also get a negatively charged oxygen. There's a critical difference between these two structures. The first is that this one, I can easily draw a resonance structure that shows that this negative charge is actually delocalized between both oxygens, and that actually makes the structure really stable. And so you might be wondering, well, why does it matter if the structure is stable? It matters because the more stable your conjugate base, okay, the more stable your conjugate base, the stronger the starting acid, okay? So these structures right here are showing us the IB form of a carboxylic acid, okay? So because the IB form is stable, this carboxylic acid is considered a UA, or it's actually considered an acid. Whereas an alcohol, if you look at the alcohols right here, its IB form, if it did have an IB form, would be right here, right, if you deprotonate it. This alcohol is actually going to be neutral to begin with. So this is a neutral functional group. And that all has to do with the fact that this IV form is very stable, making the carboxylic acid, the starting acid, very acidic, versus this alcohol right here is going to be neutral because its conjugate base right here does not have that delocalization. It's very unstable because the negative charge is concentrated on that one oxygen. Long story short, when you see alcohols, think neutral. Next is an ether. An ether you could think of is an oxygen sandwiched between alkyl groups. And so this ether is actually neutral because, first of all, I don't see any protons present. And because I don't see any protons present, that tells me that this is not an acid. All right? So it is not a proton donor. And nothing in this structure can serve as a proton acceptor. Okay, so this oxygen is not basic like a nitrogen would be, for example. And if you don't remember why, you could go back to acid-base principles from organic chemistry, but for the purposes of medchem, you just need to know that an ether is neutral, just like an alcohol. An ester looks really similar to a carboxylic acid, but instead of having a proton hanging out next to the oxygen, we actually have an alkyl group. And so this ester group right here is going to be neutral, just like everything else we've been discussing. And the reason it's neutral is, again, I don't see any proton donor here. The protons attached to the carbon, you might be thinking, oh, why can't I donate those protons? Well, if you try to remove a proton from this carbon right here, the carbon's going to end up being really, really unstable, right? So that is unheard of. To have the proton removed here, for the purposes of this class, you will look at this as an ester, okay? Or sorry, as neutral. So you will look at esters as neutral. And the reasoning behind it is it is not easy to remove a proton from a carbon, right? Because that carbon will then have a negative charge, which would make it very unstable. Versus removing a proton, as we saw up here, removing a proton from next to an oxygen in a carboxylic acid is done very easily. That proton is readily donated, and it's going to result in that stable structure. So summary, carboxylic acids look kind of like esters. The difference is, next to the oxygen in an ester, we actually have a carbon group, and that's what makes it neutral, versus having an oxygen group that would have made it acidic, like a carboxylic acid. So make sure you practice differentiating your functional groups. Another functional group is an amide or an ester amide. So an amide looks like this. So it kind of looks like an amine group, which by itself, right, if I ignore this carbonyl, if I only look at the amine, I might think, oh, that's an aliphatic amine, pKa 8 to 10, but you have to look at what's directly attached to it is a carbonyl, which is what actually makes this an amide. So this will be an amide. And you might be wondering, well, what does an ester amide look like? Ester amide is kind of like an ester and an amide combined together. So that's like this. Right? So if you look closely, you see that the carbonyl is right here. And it is shared between this nitrogen group over here and this oxygen group over here. So my ester is here in pink, and my amide is here in blue. It's sharing that carbonyl. So when you see a carbonyl sandwiched between a nitrogen group and an oxygen group, that has a special name. It's called a carbamate. I like to call it ester amide because it's easier for me. And when I see that, I also know that it is neutral. Now we're going on to our ketones and aldehydes, which are my favorite because these are really easy to differentiate and to find. So I'm going to go ahead and draw out a large structure. And I'm just making up this structure as I go, so it's not actually any real structure or medicinal structure. I'm just going to kind of draw some stuff out here. Definitely not a real structure, but just for the purposes of showing the differences between some of these functional groups that you might think are the same. Okay, so bond angles here and me drawing this structure aren't technically accurate, but that's not the purpose of this. We're just looking at the functional groups. So if you look at this structure, right, this is a ketone. Ketone is simply a carbonyl that has nothing significant next to it. It just has more carbons and hydrogens next to it. Okay, so that's a ketone. Aldehyde is the same thing, but on one attached directly to the carbon is a hydrogen, right? And so here, there's a carbon versus in an aldehyde, we have a hydrogen. But they both share the fact that they have a carbonyl. So that's a ketone. This is an aldehyde. Now where's the ester group? This is the ester group. Why? Because it has an oxygen directly, an OR group directly attached to the carbonyl group right next to it. That's what makes an ester. carbonyl next to oxygen next to R group meaning any carbon chain, basically anything you want to throw on there. I could throw on a 24 carbon chain right there. That would still be an ester. Okay? And this group up here is an alcohol combined with this alkyl chain. And lastly, let's look at pyrrole. So this is where a lot of the confusion happens. So I'm going to draw a pyrrole, and then next to it, I'm going to draw a pyridine. So here's my pyrrole. Okay, so notice how in my pyrrole I have a nitrogen. There's a lone pair drawn inside the ring, and I've got to fill that valency, so I'll put a hydrogen right there. This is a pyrrole. Okay, this pyrrole is neutral. The reason why it's neutral is because this lone pair on the nitrogen is trapped within the aromaticity of the ring. In other words, I can move this lone pair here, right? I can move this bond here. I can move this bond onto here and put a lone pair there. The point is, this lone pair is literally depicted inside of the ring, and it is within the aromaticity of the ring. So I see this and I'm like, oh, that lone pair does not look like a base. It does not look like what's a base? It is a proton acceptor. It doesn't look like a proton acceptor. Why? Because its lone pair is too busy resonating around the ring that it doesn't actually want to accept a proton. So again, the electrons would much rather resonate within this ring than to grab another proton. So if it can't grab a proton, it's not a base by definition, and so it's neutral. Let's compare that to a pyridine in red. So pyridine, we saw in the last video, is a basic functional group. And you might be thinking, well, they look exactly the same. Like, how am I going to differentiate them? They actually have some key differences. Okay, so I'm actually going to redraw that a little bit bigger, just because I really want to emphasize what's going on here. So okay, so if you'll notice in this structure, we have a nitrogen that is directly next to a double bond. Whereas in a pyrrole, we didn't have that. I'm going to redraw the pyrrole. This is my pyrrole without all the red arrows, so it doesn't seem too confusing there. But what do you notice about this structure? You notice that there's actually no double bond directly next to that nitrogen group. Okay, so really focus on the difference here. So this nitrogen in the pyridine is basic. Its lone pair is out and about. It's outside of the ring. It is not part of the aromaticity of this ring. And the reason for that is I can't actually draw any resonance structures, any valid resonance structures. You could try, but if I try moving this lone pair, for example, to the adjacent bond right here, I'm going to run into another double bond right next to it, and that's way too many bonds on a carbon. It's not allowed. For me, it's easier to just look and see this nitrogen's inside. It's further away from the double bonds, so it's neutral. This nitrogen lone pair is outside. It's right next to a double bond, and that's what reminds me. Okay, nitrogen right next to double bond, basic, pyrrole. Really doesn't matter if you remember the name of the functional group as much as how to classify it. So nitrogen next to double bond, basic. Nitrogen right here, if you look at the nitrogen really closely and you redraw the structure, you'll see that it is not directly next to these double bonds. And that's what makes it neutral. All right, in the next video, we're going to apply these concepts towards answering a more challenging question that really shows whether or not you understand these concepts. So now would be a good time to take the time to answer this question, and then in the next video, we'll go over it.